Okay, students, let's look at Chapter 15 problems. We're on Chapter 15. We're going to look at number 2, and we're on page 544. All right, so number 2 says a wave speed on a string. So we got a string, okay, is 150 meters per second when the tension is 75 newtons. So the velocity of the string is 150 meters per second when the tension is 75 newtons, okay? All right, so what tension will give us speed of 180 meters per second? So we want to know what tension will give a speed of 180 meters per second. All right, well now, if we go and look at equation 15.2, we know that the speed on a string is equal to the square root of the tension of the string divided by the linear mass density of the string, and that's all under the radical, okay? Well, there's a problem. We don't know linear mass density, do we? However, we can find it by solving for it because we have the speed and tension. So we solve for mu, linear mass density, and we wind up with this equation right here, the tension of the string divided by the velocity of the string squared. So we got 75 newtons divided by 150 meters per second squared, and what do we get? We get a linear mass density of 3.33 times 10 to the negative third, and that's kilograms per meter. That's the linear mass density, okay? So now we can just take this and plug it in, and we can find the tension. Now we can find the tension, so let's solve for the tension. Well, we have to do a little bit of algebra, but tension is equal to the linear mass density times the velocity of the string squared. So we have 3.33 times 10 to the negative third, and that's kilograms per meter, times 180 meters per second squared, and we should get, I believe it's 107.9. I think that's what I calculated. Let's see, 180 squared times 3.33 to the negative third, and we get 107.9. So we get 107.9 newtons, okay? All right, 107.9 newtons. Let's go to another problem now. Let's look at number 18. All right, so number 18 says we have the displacement of a wave traveling in the positive x direction. So we got a wave traveling in the positive x direction, okay, if you wanted to do it, something like that right there. And so it is traveling this way, which is positive x, okay? And the function of this wave, y with respect to t, x, and t, its displacement with respect to time. Notice it's being displaced in the y and x direction, okay? So actually you've got two different variables here that we're looking at. Well, 3 total, but y with respect to x and t. All right, so the function then it's given is 3.5 centimeters, okay? Cosine of what? I'm leaving out the time sign. I hope that's okay. Excuse me. Excuse me. I tell you what, let's not leave it out. Let's just keep it like the book. Don't want to confuse anyone. Times cosine, because you do multiply it. And that is cosine of 2.7x minus 92t, okay, where x is in meters and t is in seconds. What are the frequency, wavelength, and speed of this wave? Okay, so what do we do? All right, well, we have to, of course, go back to equation 15.7, and equation 15.7 tells us this right here, that we can find the displacement of a wave by this right here, our wave equation, a cosine theta of 2 pi, and this is x over lambda minus t over period. We can find the displacement of that wave. In other words, we can find out how high it is y, and then we can also find out how far down it is in the x direction too. by doing that. Now, okay, all right, so let's look at what corresponds. Of course, this is A, 3.5 centimeters is A. This right here, 2.7x, corresponds with 2 pi over lambda. All right, so let's just go over here and write it. So A is 3.5 centimeters, or we could put that in meters, and we really should, 0.035 meters. All right, and then what? Then right here, 2 pi over lambda, because it's 2.7x. Well, that's after all that's right here is after all of this. So that's equal to 2.7. And by the way, that should be radians per meter. That's called the angular wave number, okay? 2.7 radians per meter, okay? Okay, you with me? All right, and then this right here, 92 radians per second corresponds with 2 pi over t, okay? All right, everybody with me? That corresponds with 2 pi over t, because remember, all of this right here is 92 times t. So 92, it's 92 radians per second. Now, we will have to put our calculator in radian mode, okay? We will have to do that. Well, when let me correct myself. We will have to use radian mode if we actually take the cosine, okay? In other words, if we plug all this in and want to find out what y is with a given time interval and a given period and a given wavelength and a given all of this, then we will have to use radian mode. But just to find the frequency, we won't have to, okay? All right, now, so we use cosine and we're in radians, it's got to be in radian mode. Okay, so let's look now. So we want to find the frequency. I think A said find the frequency, correct? All right, well, what is the frequency? Well, we know that the frequency is actually equal to what? 1 over the period. But we don't know the period, but we know how to get the period, and the period is what? The same as saying what? We can find the period by 2 pi radians, because how do we define period? The period is the time it takes for one complete cycle, okay? So let's do some, let's look at this now. We're wanting to find the frequency now. So let's look at what will correspond here. What corresponds, which of these has period in it? Do you see that right there? Notice this right here is what? Is 92 radians per second t, okay? So what we could do here then is come in and say 92 radians per second divided by, notice this is 92 radians per second t, all right? Well, we just plug in for the period, which is 2 pi radians, because that's how long it takes to complete one cycle. And what do we get? Well, we get 92 divided by 92 divided by 2 times pi, and you do need to use pi. Oh, I forgot to put it in parentheses. 92 divided by 2 times pi. And we get 14.6 hertz, okay? 14.6 hertz is the frequency. You say, how do you know? All right, look, 92 radians per second t is 2 pi over t. Well, we don't know what t is, so we say, well, we know one complete revolution is 2 pi. We got to cancel the radians out, folks. You follow me? We got to cancel the radians out. So radians divided by radians is gone, and we're left with 1 over s, and 1 over s is a hertz. So 14.6 hertz. All right, now let's look at B. B says, what is the wavelength? Well, we know from right here that 2 pi over lambda is 2.7 radians per meter, right? Yes, it is. So let's solve for lambda, okay? Well, if 2 pi, let me just write this, 2 pi over lambda, according to our, and you say, where are you getting that? Look right here, y'all. Look right here. I'm getting it from my, oh, please tell me I didn't delete it. I'm getting it from my general equation. This is the general format for the wave equation, all right? That's lambda right there, by the way, lambda, okay? All right, which is equal to what? 2.7, and that's radians per meter, isn't it? Yeah. All right, so let's solve for lambda. Well, okay, lambda then is going to be equal to what? Well, lambda, and of course you're going to have to flip everything. So lambda then becomes what? Lambda's on the bottom, so really what you need to do is flip it over first. I'd flip this over first and make it lambda over 2 pi. And of course you got to flip the other side over too and make that 1 over radians per meter. Okay. So 1 over 2.7 radians per meter. And so lambda then is equal to what? 2 pi over 2.7 radians per meter. And what do you get? Okay, well, you get 2 times pi divided by 2.7, and you get 2.327. We might round it up 2.33. So we get 2.33 meters, okay? So that's how you do the wavelength, okay? All right, real easy, okay? So you got to think about what you, again, you can't forget this general waveform. That's the wave equation, and that's just a general wave equation, okay? That's what you use to solve for the displacement of a wave, okay? And then you just look at your parts and look at what coincides, corresponds with it, and then you solve it, all right? And now let's look at C, part C. What is this, 18C? All right. Well, we know that we can find the wave speed, and the wave speed's easy. Velocity is equal to what? Well, it's equal to, we've already had this equation, lambda times the frequency. Well, what was lambda? Well, lambda was 2.33 meters, okay? And the frequency was 14.6 hertz. This is real easy. And so then the velocity of the wave, or the wave speed, is what? Well, we get 2.33 times 14.6, and we get 34.01, don't we? So 34.01 or 0.02, so it'll be 34.02 meters per second, okay? You say, now how do you know it's meters per second? Because that's hertz. All right, look, meters, that's like saying meters over 1. Hertz, y'all, you got to remember that hertz is reciprocal seconds. It's 1 over s. Remember, y'all, that the frequency period is the time for one cycle, the time it takes to complete one cycle. Frequency is the number of cycles in one time period, like 1 second. So the number of cycles in a second. Period is the number of cycles. Period is defined as the time it takes to complete 2 pi radians, 1 complete cycle, okay? All right. Frequency is the number of cycles in 1 second, okay? All right. So there you go, okay? And let's look at one more. All right, number 40. We'll go to a clean slide. Okay. What is the sound, and by the way, this is on page 546. I think that's right, yeah. So it says, what is the sound intensity of a whisper at a distance of 2 meters in, I'm sorry, I'm reading the wrong problem. What is the sound intensity level of a sound with an intensity of 3 times 10 to the negative 6 watts per meter squared? Okay, watts per meter squared. So what is the sound intensity? What is the sound intensity level of a sound with an intensity of 3.1 times 10 to the negative 6 watts per meter squared? Okay. All right. So let's look at this one and make sure we read it right, and got to pay attention to what we're reading. Okay. Always take your time and make sure you're reading the question properly. Okay. All right. All right, let's see here. Let's write out our values here. So we have equation. First of all, we're going to look at equation 15.14, and the equation for that is the intensity, sound intensity, is equal to 10 of dB, decibels, dB, log 10 of what? The intensity over the initial intensity, or the threshold, all right? I over I naught. And so we just plug everything in, y'all. All right? So we come to what? We have the intensity is equal to, well, it's 10 dB, decibels. And it's log 10 of what? Well, the final intensity, or the intensity we're interested in, is 3 times 10 to the negative 6. So that's 3 times 10 to the negative 6, and that's watts per meter squared, divided by 1, which is the initial or threshold, of 10 to the negative 12th. And, of course, your units cancel out. And so what do we get? Well, when we do all this ungodly arithmetic, what do we get? Well, we say 10 log of what? 3 to the negative 6th divided by 1 to the negative 12th. And what do we get? We get 64.8 dBs, decibels. So that's your sound intensity level, okay? 64.8, or if you wanted to carry it to the two significant figures, 65, okay? All right, that was real easy, wasn't it? No, so you say, well, how'd you do that? Well, you just type it in like you said. You say 10, and then you hit the log button on your calculator, and then you put a parentheses bracket in there, and then you put 3.6 to the negative 6 divided by 1 times 10 to the negative 12. Close your parentheses, it equals, boom, and you got it, all right? Okay, I hope this helps.